Okay, I think we can go ahead and get started. So for the rest of the day, we had a few topics lined up. I'm going to go back to the agenda really quick, and let's see, and just go over what we covered so far. Okay, so we are notionally around here. And Greg has already covered build systems, so I'm going to skip build systems. I'm going to start with environments, and then I may cover a little bit of build systems if we have enough time, or if it looks like we have enough time. And then I'm going to do advanced packaging. And I think we're probably just going to punt on the extra time at the end and use all the extra time that we have tomorrow for this. That was padding anyway. So that's where we're at. So if you want to get synced with us, go to bit.ly/Spack tutorial, which is written here, the only place I can write anything, and skip to the environments section of the tutorial, and that's where we'll start. So go back over here, and if I pull up, okay. Read it carefully, Greg. It says they can use your name to promote anything having to do with the University of Oregon. Pretty awesome. What? Greg Becker endorses this. Yeah. Okay. So we've seen how to install and remove packages with Spack, and we've seen how Backfind displays the packages that are installed. It is pretty ridiculous, isn't it? Yeah. Yeah, not Spack, but the waiver that we're signing for this presentation. If you see anything about Spack on Oregon branded things, we totally signed off on it because we signed this waiver. If Spack is used to endorse anything having to do with the University of Oregon, it's completely legal, and we have waived our right to do anything about it. All right. So if you type Backfind at this point in the tutorial right now, it looks like this, and there are a ton of packages installed, right? So we have like cfizio, zlib, all the stuff that we installed before, lots of versions of HDF5. And I think actually if you compare this with what's on the environments page in the tutorial here, it's actually longer because Greg did the module section first. Oh, that's not good. Okay, let me start over. That is, get out of end show. Okay. All right. Okay, that's better. All right, so I'll start over. If you type Backfind at this point in the tutorial, you'll see there are tons of packages installed, and this is a pretty cluttered view, right? There's a lot of different versions of things. There's different HDF5s built with different MPIs. Backfind provides this high-level grouping of things by their platform OS and target architecture and the compiler that was used for them, but it's not really showing you the full information about the dependencies under here. It gets a little cluttered once you have a lot of things installed with Spack. And we saw that you can use Backfind to query things and to sort of filter this view down. So you can say, show me everything that was built with MPIG, show me everything that was built with OpenMPI, if you want to. But there's another mechanism that you can use in Spack now that makes this a little bit simpler. You can have essentially virtualized sub-environments in Spack with Spackenv. And so that's what we're going to talk about here. So if I want to make an environment in Spack, I can just type Spackenv create my project like this. And I'm going to move this so you can see what I'm doing. All right. Although I want to see the clock too. So all right, so I'm going to say Spackenv create my project. And Spack will say, okay, I made an environment called my project in this directory. And so that's basically where the state of the environment is going to be stored. This is basically a virtualized Spack instance. And you can see what environments are available like this. So you can say Spackenv list, and it says, okay, you've made one environment. It's called my project. And then if we actually want to use that environment, we can say Spackenv activate my project. And so once we say that, things are going to look a little different. So if I've activated this environment, I can now say Backfind, and it looks like nothing's installed, right? And don't panic. This is just we're in an environment, and so that's why it says in environment my project here at the top of Backfind, so that no one freaks out and thinks that all of their stuff has been deleted and is no longer installed. We tell you that you're in the environment, and now there are 0 installed packages. And so I basically have my own new clean instance of Spack to play around with. So if I say Spack env status, I can always see that I'm in a particular environment too. It'll just tell me which one I'm in. So this just says you're in environment my project because you activated it. And then if I want to get out of the environment, like if I want my giant list of packages back, I can do two things. I can say despacktivate, which is an alias that got set up. So we had to do that. We were debating whether to do the despacktivate thing, and we kind of had to go with it. So you can say despacktivate, and then you're out of the environment. And so now if you say Spackfind up here, you're no longer in the environment, and you can see the full set of packages that you had installed before. You can also, if you don't like despacktivate for whatever reason, it's nice because it's an alias and the tab completes pretty well. But you can say Spackenv activate my project like this, env status. You can see you're in my project. If you don't want to type despacktivate, you can just say Spackenv deactivate, and that's the same thing. One's an alias for the other. And so now if I type Spackfind or Spackenv status, you can see I'm not in an environment anymore. Okay, so with all of that, let's go back into the environment. So let's do Spackenv activate my project again. And now I'm in the environment. And again, like if I type Spackfind here, there's nothing. But if I now install something, if I say Spack install tickle, then it's going to say, oh, it's already installed. And so I'm going to go and grab it. Or it's going to say zlib's already installed. It's going to try to install tickle. It's going to go here. And oh, wait, I don't have the trust set up. Let me reconfigure my mirror. So Spec, mirror, add mirror.
Give it a name first.
Oh yeah, sorry.
Already there. It's your configuration was off.
Can't see anything because Samir has joined the meeting. All right. Okay. So the mirror is trust. Hey, Greg, is there anything special from the module tutorial that I should remove before I go on with this?
Module config.
Yeah.
Delete it.
Yeah. That one? Okay. So if I say Spack install tickle, what happens? This should not try to build. Hold on. Do we customize anything in here? So here, compilers, repos. Oh. Actually, yeah, Spec, compilers.
Yeah.
This one. Okay.
Yeah.
Sorry, I had the extra GCC compiler loaded from the.
Everyone else will have it loaded from the module tutorial.
So everyone should just type Spack compiler rm GCC at 720, so that that's not in your Spack compilers list. Otherwise, the specs won't match up for this part of the tutorial, and you won't get the binary caches. So everyone do that. I've already done it. So now, okay, back to my environment. Now I'm in Spack env list, Spack env status. I'm in my project. So now if I say Spack install tickle from here, it'll say tickle is already installed there. And now if I say Spackfind in the virtual environment, it says, okay, your root spec is tickle. This is what you asked to install. This is what you've explicitly asked for. And then these are the installed packages. And what you can see here is that the roots are basically, this is the requirements. This is what you asked for. This is what this is the requirements for the environment. The installed packages is that plus all the dependencies that were brought in. And so it's maybe hard to see this from here, but tickle here is blue and zlib is white. And so it's highlighting all of the root specs down here. So anything that's white down here was brought in as sort of a transitive dependency. And anything that's blue is the concretized root spec from up here. Yeah?
Will the brought in packages include build dependencies or just run dependencies?
Build dependencies as well.
Okay.
Right now. Yeah. Okay. So once you've done that, now you can see you have a tickle package. Let's also install Trailing here. Spack install Trelinos. And it'll do all the things that it usually does. It's going to find the build caches. It's already downloaded all these things. And it's going to go and install those. So let's give it a little time. Let's figure all that out. I think we actually removed that Trelinos earlier. Right? Yep. So now if I type Backfind in my environment, you can see I got two root specs. So I've got Tickle and Trelinos. Tickle and Trelinos down here are still highlighted in blue, right, because they're the roots. And then you can see all the extra dependencies that were brought in to support those things. Any questions? Nope? Okay. Okay. So we've done that. And now let's get out of here and let's create another project. So I'm going to say despacktivate on this environment. And now if I do spackenv status, you can see I'm no longer in that environment. And I'm going to make a second project. So I'm going to say spackenv create my project 2. And now if I do spackenv list, you can see that there are 2 environments. And I'm going to spackenv activate my project 2. Okay, so now if I do Spackfind, I'm back to having nothing, right? Because I just made a new environment, and now I got into it. And now I'm going to install some slightly different things in this environment. So I'm going to say Spack install HDF5 now. Okay, and it says, okay, you've already got that installed. We'll talk about what that means later. And we're going to say Spack install Trelinos here. Okay. So now if I do Spackfind on this, you can see I've got 2 root specs just like in the other environment. HDF5 and Trelinos, the root specs are highlighted sort of like before, but it's HDF5 instead of Tickle. And all the extra dependencies are in there as well. And so there's basically 2 environments, one with Tickle and Trelinos and another with HDF5 and Trelinos. Okay? So if from my project 2, I now say Spack uninstall Trelinos, I can do that. It's going to say, okay, do you want to install that Trelinos? And I'm going to say yes. And now if I do Spackfind in my project 2, it's just HDF5 and all of its dependencies that are left. Okay, so it actually pruned the transitive dependencies of Trelinos out of that environment, kind of garbage collected them. And I've only got 8 installed packages left. And so if you're following, you may wonder, what happened to Trelinos in the other environment, right? Because I had 2 environments, both of them depended on Trelinos, right? They both had roots that were pointing to Trelinos. And so if I despacktivate this environment and I spackenv activate, whoa.
So we need a spactivate.
David was just commenting about the lack of symmetry and how disappointing it was. So yeah, we may need Spacktivate. We could add that. If anyone wants to add Spacktivate, you could stick it in setupenv.sh. Yeah. Oh, yeah. Well, you could move it. You could contribute it back. You could be a contributor.
I already did.
Yeah. All right. Okay. So we're going to go back to my project 1, the first one. I guess we don't have tab completion on project names yet. So now if I type Spackfind, you'll see that Trelinos is still there. So this is the first environment I made. I installed Trelinos and I installed Tickle. And in the second environment, I installed HDF5, I installed Trelinos, and I removed Trelinos. So what's going on here is that Spack is smart enough to realize that this Trelinos right here is still needed by one of the environments that it's managing. And so it won't go and just fully remove the package. If something is needed by an environment, Spack will warn you about it and it'll say you can't remove that. And if you just uninstall it from an environment, it'll remove it from that environment, but it won't remove the actual installation. And so I think, what's really going on here is that the environments are sort of, they're wrappers around the installs of Spack. They're all sharing installations. You can have lots of different environments that share certain packages. And Spack will keep track of which environments need which packages, and it'll remove them when no more environments need a particular package. So, if I go on, any questions about that so far?
So if you're not in an environment, you delete Trelinos, what happens?
It'll complain if a managed environment needs Trelinos.
Okay.
Okay, so
It's kind of like iNodes.
It's reference counting.
Reference counting.
Yeah, and so it knows when environments need that particular installation, just like it knows when dependencies need that installation. You can still force uninstall it, and then the environments will be broken. So yeah, we don't prevent you from shooting yourself in the foot. We gently ask you not to. Okay. So if I want to deal with a lot of different specs at once, I can also do that. And I guess just for reference here, when I've typed stack install here, it seemed really quick because you know, I already have all these things as binary caches, right? When I'm installing a bunch of things from source, it's handy to just say all of the things I want at once and then install them all at once, as opposed to having to say stack install foo, stack install bar, and so on. And so one of the things that you can do with the Spack environment is, like, see how we have these root specs and we have the installed packages? You can build up your root specs independently of installing any of them. And so that's what I'm going to show right now. So if you go back to the first project, which I already did, I'm in my project. So everyone go back to the first project. You go Spackend status. You want that to say in environment my project. So if you are in my project 2, deactivate it and then go into my project. And so now I'm going to add some more things to this environment. I'm going to say Spack add HDF5. Note that this is add, not install. So I'm going to say add HDF5. It's like, okay, I added HDF5. Spack add GMP, Spack find. So the interesting thing here is that now I have root spec right here. GMP, HDF5, Tickle, and Trillinos. And I have some root specs down here. So Tickle and Trillinos show up, but there are not installed versions of the ones that I just added, so GMP and HDF5. And that's intentional. That's so that you can build up these things gradually. And if you want to install all of the stuff in the current environment, all you do is you just type Spack install with no arguments. It concretizes the whole thing, installs all of those things. And now if you type Backfind, you've got GMP, HDF5, Tickle, and Trillinos are your roots. And then you have Tickle and Trillinos down here, and also GMP, HDF5, and all of their dependencies. Make sense? So I've just added some new specs. It's a way to do a bulk install of a bunch of different packages. And I have a clean environment that lets me see all the stuff that I installed for those packages.
A question?
Yes?
Are the packages in the different environments like actually replicated, or are they like soft links? Or...
They're soft links.
Okay.
And so, and actually, okay. So for the command line tools in Spack, they're not even soft links. It basically, there's an environment variable called Spackenv that tells you which environment context you're in, and we'll see how the state for the environment is managed. It's intentionally done with files that are hand editable, and so we'll talk about that at the end of this section. If you pull down the latest developed version of Spack, what actually happens with the environment is that everything in the environment is symlinked into a single directory, and so you get one prefix with all the stuff that you have in your environment, and you can load that like a module, right? So it works like virtual env. So you can have, basically, it's like virtual env, but for anything, not just Python, right? And so you can have a bunch of different environments, each with their own prefix that you can load, and then you can activate that, and it goes in your path, it goes in your LD library path, and all of that stuff, so you can actually build against it. And it's pretty convenient. So I use that for like my Python stuff. I'll just Spack install, you know, NumPy pandas and all that stuff that I need for an environment. I'll activate it and I'll just work in that environment, and then I'll do another one on the side. So that's what's really going on here. In the 0.12 release, we don't yet have the view creation for the environment. So we don't get the sim linking into a prefix, but we do have the isolation of the command level. Maybe that's too much detail. Okay. So let's see, I'm here. Okay, so the other interesting thing about an environment is we saw in the configuration section that there's a lot of configuration that you can do for Spack, and you know, it's fairly global the way that we've shown you how to do it so far, right? Like you can have etc configuration, you can have a Spack instance configuration, you can have configuration in your home directory. Environments also give you another configuration scope, but just for that environment. And so what you can do in an environment is if you want to associate some configuration with it, like let's say I want to say Spack spec hyper in here, right? If I say Spack spec hyper, what I'll see is that hyper gets concretized with OpenMPI as its MPI for this environment, okay? And that's okay, but you know, what if I want to change that behavior? So if I do spack config get on this environment with no arguments, right? We learned spack config get earlier, and it'll dump a config section. But if I do it with no arguments, it's basically implicitly giving me the configuration for this environment right here, okay? And so this is just saying there are these specs that I want to install, and I can actually edit that. Any questions? Okay. So if I go spack config edit inside of an environment, it'll take me to this file, and we'll talk a lot about this file later. But here, let me clean up this format a little bit. This is just basic YAML, and this is equivalent to what was there before. I just like this list format better. So I've got those specs. Those are the specs that I'm going to install. And now I want to add something to this so that I can, so that I prefer another MPI. So within this environment, I'm going to say my packages are, for all packages, I want my providers for MPI to just be mpitch. So now I want, basically, when I'm in this environment, if I install something and I have to pick an MPI, I'm going to pick mpitch instead of OpenMPI like was happening before. So if I get out of here, or actually, let's just get out of here, exit the editor. And now I do spec hyper. You can see that that took effect. So now hyper gets concretized with mpitch instead of OpenMPI. And it's just in this environment, right? So if I get out of this environment and I run the same command again, I'm back to OpenMPI, right? So if I say spec hyper after doing a despacktivate, it goes back to the default. But if I do spec and activate my project, now I'm back to here, and I do spec hyper, you'll see that it's using that mpitch that I just configured it with. Okay, so I have a way to set a context not only for a set of packages that I want to install, but also for the configuration that gets associated with them. So it's pretty versatile. You can have a lot of different Spack environments configured different ways, and you can experiment with different settings without just completely polluting your global configuration for Spack. Any questions? Cool. All right. So the thing about that is that if I run Backfind here in this environment, right? I installed all of these other things, GMP, HDF5, Tickle, and Trilinos, right? I installed those with the MPI set to OpenMPI. Okay. So I can, if I do the find-l, and if I really look at this HDF5 that I installed, right? I do spec. I'll just do spec on its hash, right? Show what that is. You can see that HDF5 is actually built with OpenMPI, right? But I've since changed my settings, right? I changed my configuration. One thing that you can do with Spack environments that we didn't allow at the global scope very easily is you can reconcretize the whole environment. So you can basically just say spack concretize -f on this environment, and we'll go and concretize all the roots again and write the configuration. So now if I do a spack find, what happens is I've only got a few of the roots installed. So I have Tickle, Trilinos, and GMP because I had versions of those already. And HDF5 isn't there anymore because I had asked for the version of it with mpitch instead, and it's not currently installed. So now if I look at the things that are in this environment, so if I do spack find -l again, and I look at this Trilinos here, let's see, I'm gonna grab this one, and I do a spec on that. It's a different hash than it was before, and now it's built with mpitch and not OpenMPI. Right, so I basically reconcretized everything in the roots, and I basically just said switch this environment from using OpenMPI to mpitch, right? But keep the specs the same. Okay, and now if I want to install all of that, I can actually run spack install again, right? And this is interesting. It's trying to build HDF5 manually. I'm going to stop it. But the reason for that is that the root for HDF5 is just HDF5, and I actually don't have a build cache for HDF5 with mpitch. I have a build cache for HDF5 plus HL with mpitch from the first part of the tutorial. So I'm going to spack remove HDF5, right, from my environment. And if I do a spack find now, that just removes the root, okay? And if I do a spack add HDF5 plus HL, which is the one that I happen to know that I have a build cache for, I've replaced the root. HDF5 plus HL is in the environment. If I do Spackenv edit, you can see here that now there's HDF5 plus HL in the configuration, right? That's what I'm going to install instead. So I just changed what was in the environment spec with remove and add. And now if I do a Spack install on this environment, it's just going to say, oh, I've already got that. And now I've got everything that I asked for. So I've got GMP, HDF5, Tickle, and Trillinos. And then down here I've got GMP, HDF5 has been concretized and installed, and I've got Tickle and Trillinos as well. So now I've got the whole thing in my environment. And so it's an easy way to basically take a set of specs that you've concretized one way, and then tweak something about the configuration, reconcretize the whole thing slightly differently, and then and build it again. Any questions? Okay. So the other thing about environments is, so far I've shown managed environments. And what that means is basically that if I say Spack env list, Spack knows about these environments. They have names. I said Spack env create my project 2. I said Spack env create my project. And that's fine. I mean, that's handy from a command line perspective because I can give names to my different contexts that I care about. It's good for experimentation. I'll use this, like, if I'm debugging things for Spack, I'll create an environment with the GitHub issue number and replicate the issue in the environment, and then keep a few of those live as I'm working on different issues. You could do the same thing if you're working on tickets for users or something, or if you're trying to replicate what a user wanted to do. You could maintain multiple environments at once and understand their particular context. So the environments themselves are they're not really they're not some opaque thing that Spack manages. They're actually designed so that the configuration and all of these settings can be edited by hand in files as well. And so if I go over here and I do Spack cd-e my project, this will cd to the directory where the environment lives. Okay? And so now I'm in this directory here. So I'm in home Spack2, so that's my user. I'm in the Spack instance that I cloned earlier. And all of these managed environments, like my project and my project 2, they just live under var Spack environments in the Spack installation, right? So they live in a subdirectory of your Spack install. And if I do an ls here, I'll see some interesting things. There's a Spack.yaml file, and there's a Spack.log file. And so we're going to talk about what those things mean. So if I cd in here and I edit this Spack.yaml file here, this looks familiar, right? This is the configuration we were editing before. Yeah.
Sorry, I don't mean to derail. Does this mean that I can have a Spack environment specified as such without actually installing anything?
Yeah.
And push that out as a system administrator, and only when this is invoked to then build that environment?
We're gonna get to that in a couple scrolls.
Sorry.
All right. So this looks very familiar. This is what we configured earlier, right? It's the same syntax that we used when we did Spackconfig edit. Spackconfig edit inside of an environment just takes you to the Spack.yaml file for that environment. That's all it does. And the cool thing about this file is that it's a merged version of the Spack configuration you saw earlier. There's packages.yaml, repos.yaml, mirrors.yaml, all of those different settings. You can put those settings in one file in an environment and have everything versioned at once in a way that you could like hand to someone. So you could just email someone a Spack.yaml file and they could try to reproduce your environment. So let's see. The other thing that this means is that I can actually have environments that aren't managed. And by managed, remember, I mean that the environment lives within Spack and has a name. So I could actually go to my home directory here. I'm just going to, and there's, the only thing here is Spack right now. If I do make dir code, right, and I cd in there the code, nothing in there right now. But if I do Spack env create -d dot, that means create an environment in this directory right here. And so I can say that. And if I do an ls now, all it's done is just put a Spack.yaml in that directory. I could have even written that by hand. And if I look at what's in there, it's just an empty environment, right? And so it's just, that's basically the specs list is empty. There's no other configuration associated with it. This is where I would add packages if I wanted to add things to this. And so the other kind of cool thing here is, like, let's see, is that if I'm in this directory Spack considers this environment to be active. If it sees a spack.yaml in the current working directory, it'll say, oh, you're in that environment. And so you can use this to basically associate configuration with like a directory in your file system or a Git repo or some context that you want to have some package installations associated with. And so if I do Spackfind here, it'll say, you're in this environment right here. And instead of showing a name, it says you're in home spack2 code, which is just the directory path. So you're in that environment, and it's treated basically the same as the ones that we already showed. And if I edit this spack.yaml file and add some packages, right? Like if I add boost, Trilinos, our favorite, and OpenMPI to this environment, right? Now if I say Spackfind, you can see that just updates the roots. That list is the roots for the environment, right? And if I say Spack install here, it'll say, okay, I'm installing for this directory right here. And now if I say Spackfind, I have a Spack environment that includes all that stuff. And so it's just like using the named environments. It just happens to be versioned in a directory. So you can basically just send Spack configuration to other people by shipping around a Spack.yaml file. Okay. So skipping ahead a little bit after that, let's see. I'm going to just skip straight to the Spack.lock part. The other thing that you'll notice here is that now that we've installed this stuff, there's another file in the directory, and that's the Spack.lock file. And so that file is interesting because it contains the complete concrete configuration for the environment. So it basically, that's everything that came out of the concretizer for these specs. And so if I edit that file, I get this, right? It says concrete specs, it lists their full hash, and it says here's XZ, right? It has version 5.24, here's the architecture information, here's the compiler it was built with, here are all the flags, and then here are all of its, and then here are the other specs in the environment. There's Perl, you can dig through here, you can even see like the SHA-256s of patches that were applied to this, to these things when they were built. And so these are two different views of essentially the same thing. So Spack.yaml you can think of as the equivalent, for an environment of an abstract spec. So if I were to say Spack install HDF5 on the command line, right, or Spack install HDF5 at 5.2 or whatever, I don't even know if that exists. But if I said that, that's an abstract spec. It doesn't have all the details filled in yet, right? And so Spack.yaml is a specification of what you should build. It's the requirements. And then Spack.lock is the equivalent of a concrete spec, like we showed earlier. When you take that abstract spec, you run it through the concretizer. Every detail that got filled in by Spack gets spit out in this Spack.lock file. And you can actually reproduce an environment for either of those. So if I wanted to make another environment, like if someone sent me one of these files, right, and I make another directory called, so Spack env create, find the syntax here. I'm going to call this one my project for a directory, and let's do /my project. And I'm going to create it from the Spack.yaml in code, right? What am I doing here? Oops. Doing a little unnecessary syntax check. Right. Oh, I'm creating an environment with this name that's managed from this Spack.yaml file. And now if I do Spack env list, I've got three projects. I've got my project, I've got my dash project, I've got my project, and I've got my project too. I could also just recreate it in a new directory. So I could do Spack env create -d new code from code/spack.yaml like this. And then if I cd into new code and I do a Spackfind here, you can see that what I got from the other environment is just the roots. So if I cat the Spack.yaml, I've just got what was in that YAML file, right? It's just the abstract version of the environment. And I can reconcretize that in a new platform. So I could say Spack install here. It'll go and do everything that it did for the previous environment. And so some user could basically take your Spack.yaml and reinstall everything that they could recreate your environment. But they may recreate it in a slightly different way. So if your Spack is configured differently for a different platform, this is kind of a way to represent cross-platform package configuration. So like one example at Livermore that we've been thinking about is we deploy Jupyter for our users, and we have Power and Intel machines. And right now, if you make a virtual environment in Jupyter and you expose that to users, we have a shared file system for both of those machines. And so if you create the environment on the Power machine and try to use it on the Intel machine, it explodes. If we we could use something like this to abstract that. So basically, instead of writing a Python virtual env, the user would basically just use a Spack.yaml file to specify the environment at a high level so that they have their requirements. And we could actually use that as an environment across 2 different platforms. We're thinking about doing something like that with our Jupyter install.
So on the testing side, continuous integration or whatever, you can almost basically do the same thing as far as basically you're copying the YAML file. But then if you also want to vary it, you could also do a parameter study for build parameters on different things to kind of do comparison.
Yeah. And so like we're going to talk about this a little more tomorrow, but Spack stacks are an extension of this format, right? And so the stacks that we're going to talk about for ECP deployment tomorrow are basically a way to have a unified software stack specification across architectures, right? So I can have my spec for all the things I'm going to build for ECP in one environment. And that's a Spack.yaml file that says, here's the requirements for ECP. This is the ECP software stack. If you want to install this on multiple machines, then you just go and concretize this Spack.yaml on the different machines and build it, right? And you know, I can pass that around as a file. The other file in here that's interesting is the Spack.lock file. So if I want to exactly reproduce the environment that I made before, right? So I had code. If I ls code, I had concretized and installed this thing, right? And it has this Spack.lock file that has all the details from the environment. Now if I do Spack env create-d, we'll call this /concrete, and we'll create it from code/Spack.lock, right? That's a way to copy an environment exactly. So instead of taking the abstract configuration, which is basically just the high-level requirements, I'm taking the full build configuration. And so now if I cd into there, and if I do Backfind, I get everything from the previous environment, right? I get not only the roots, but also the concrete specs, and so it's an exact replica of what was built before. It's going to build with the exact same configuration, as opposed to just reconcretizing the requirements. And so I think that notion of just abstract versus concrete specs is pretty powerful, because the abstract thing is basically portable, but the concrete spec provides, or the Spack.lock provides a way to reproduce something exactly on the same architecture. Any questions? Yeah.
If somebody messes around with installations on the base Spack install, does that break your environment, or is there any other management for that?
I mean, if you try to uninstall something in the base Spack install and the environment is managed, then Spack will tell you that you can't uninstall that thing, or it'll warn you, and then you can, if you then mess with the installation, yes, it'll affect the environment, because there's no more installation, right? They all point at the same installation. Okay, so that's it for environments. Any questions on that? Nope. Okay, cool. All right. So I think I'm going to go through the build systems a little bit more. 4:38. What time do we finish in here? 5:30?
So our next event, the dinner is at 6:30.
Okay, I'm not going to drag this out to 6:30.
Yeah,
I think people would murder me. It's
whatever,
been a long
whatever
day.
you want, they can go for a walk and then
Okay.
go for dinner at 6:30.
Well, okay. I will go through the build systems, and then I think I'll do an overview of the build systems, and I'll do an overview of the advanced packaging stuff. And then I think we can call it a day. Yeah.
We did the slides for the build systems earlier.
Did we do all of them?
All of the slides, yeah.
Yeah. Oh, okay. So we already did. So okay. Then I'll give an overview of advanced packaging. I don't think I'm going to go into the details of the tutorial for advanced packaging, because some of it is kind of tedious, and I think you can get the idea from the slides. So I'm going to just go through that at the slide level. Here we go. So for advanced topics and packaging. All right. So Greg showed you how to make basic packages. Spec also tries to automatically configure packages with information from dependencies. And so, like, we talked about the compiler wrappers that Spec uses, where if you say Spec install, in the build environment, you'll get compiler wrappers around all your compilers. It'll add -Ls and -Is for your dependencies to the command line. And in many cases, stuff will just work. So, like, a lot of AutoTools builds, maybe not NPI leaks, as Greg demoed, but a lot of them will just act like the thing is installed on the system if they see that the compiler is passing a -L and a -I. In some cases, though, you do need to get specific information from your dependencies. And so Spack has interfaces for this at the package level. And so there are a couple questions you can ask inside of your packages that are useful at build time. So things like, how do I retrieve dependency libraries and headers when configuring my package? By default, like I said, Spack puts the library search paths on the command line, and if the build system knows what libraries it needs, then that's fine. But sometimes for things like BLOS builds and for LOPAC builds, you actually need to explicitly pass the libraries for the dependency, and say you want to build with this particular BLOS library. Do you have a question? Oh, okay. You can keep your arm up. It's cool. I'll just remember. Okay. And then how does Spack help me configure my build time environment? So that's the other thing that we want to answer here. Is how do you have a package like a dependency actually pass information up to the dependent and say, here's how you build with me, right? So that's what we're going to talk about here. All right. So in Spack, to access dependency libraries, we have some syntax that you can use inside the package that lets you access the individual library files that are provided by a dependency, okay? So if you have a package like this, rpack-ng, right, this is just a package. It depends on BLOS and LOPAC, right? And it turns out there are lots of different BLOS and LOPAC implementations, right? So you might have MKL, you might have ESSL, you might have just netlib LOPAC or netlib BLOS. You don't know which one it is because you've depended on these things through virtual interfaces, right? So you said, I just need BLOS. Get me BLOS. Get me those symbols. In the install method, you don't have to get down into the details of these things. You can still refer to them abstractly and get the specific libraries that have to do with that particular installation. So it's, in a way, this is sort of like polymorphism for Spack. And so here what we're doing is we're saying, so this is the install method for rpack. When we go to install rpack, we know that all the dependencies have been built beforehand, right? Before this install method is executed, right? And we know that the DAG, the concrete dependency graph, comes in as this spec variable here. And we're supposed to get this installed into prefix. So the first thing that we do is we go and say the LOPAC libs equals spec sub lopac.libs.join semicolon. And so the key thing here is that this spec object, right? We know from Greg's part of the tutorial that you can access your dependencies and certain things about them by just saying spec sub name, right? And the unique thing here is that you're saying spec sub lopac, and that's a virtual dependency. And so you're saying spec sub lopac. What may come back is, it may be BLOS, it may be netlib BLOS, it may be ESL, it may be MKL. Regardless, it supports this libs method here, right? And so you can ask that lopac implementation to tell you what the libraries are for it. And then we provide some convenience methods like join that join all the libs together with like semicolons for CMake, or with dash capital L flags if you want to put them on the link line, things like that. And so this is what that looks like. So you can get the LOPAC libs this way, you can get the BLOS libs this way, and then if your particular build, like rpack does, requires the LOPAC libraries and the BLOS libraries, then all you really have to do is pass them in as a string like this, and you're done. And now you have a build recipe that works with lots of different BLOS implementations, but it uses the same code. It's single source and it's portable across those different things. And so this is another example of us templating packages. So this is what's really going on here, and actually it's interesting because this works even if you have weird configurations for LOPAC and BLOS. So what I mean by that is, depending on the implementation, you may actually have the LOPAC and BLOS as separate packages, right? So in this configuration, rpack-ng is going to build with netlib LOPAC, right, which is just kind of a generic pack, and it's going to build with ESL, right? And this is installed in one directory, this is installed in another. We're using the LOPAC interface here, and it's calling into this BLOS, and we're using ESL for BLOS. So your providers are two different packages, right? This is providing LOPAC to rpack, and this is providing BLOS to rpack. And so when you say spec sub lopac.lib, spec sub lopac returns the LOPAC provider, which is netlib LOPAC. And when you say spec sub BLOS.lib, this returns the BLOS provider, and then you get the libraries from both of those different places, right? And you use the same code. Over here, with rpack might be built with netlib LOPAC minus external BLOS, which is an option, which means that netlib LOPAC is going to have its own BLOS built in, right? And so now you don't have ESL in there. You just have netlib LOPAC, which is providing both LOPAC and BLOS. But the code in your package can be the same. And so you can basically say spec sub lopac.lib. It says, oh, well, netlib LOPAC is providing the LOPAC interface. I'll return the LOPAC libs. And you can say spec sub BLOS.lib. And in that case, it says netlib LOPAC is the BLOS provider. It'll return the BLOS libraries. And so, if you look at this from a Python perspective, the weird thing going on here is that, in Python, you would imagine that this spec sub LOPAC would return the same object as Spec sub-BLOS. It actually doesn't. Stack puts a wrapper around this so that it knows in what capacity it's being used. So we're going to give you a wrapper around the spec for this thing that says, I'm a BLOS provider, or I'm a LAPACK provider. And then that provides the libs attribute there. And so basically it just lets you use the same code for lots of different configurations of the same library. And the virtual dependencies, it doesn't matter if they happen to be coming from the same package or from different packages. You can build your package the same way. Any questions about that? Yeah.
You might be getting to this, but are we going to see how Spack figures out what libraries and search paths are provided by these functions?
Yeah, it's in the tutorial. I don't think we actually get to it in the slides, but I'll show it right now just for reference. So like the way that we do this is you just define, so this is in the advanced packaging tutorial towards the end. But if you want to provide that information as a, and I guess you can't see this, but if you want to provide this kind of information as a dependency package, then what you would do is something like, let me get out of this slideshow. Something like this. So all you have to do is provide this property in your package. So if you know that your package is a LAPACK provider, and that it says it provides LAPACK, and you want to provide a special set of libraries for LAPACK only, this is all the code that you have to write. You just define this method called LAPACK lib, you mark it as a property, and then basically you go and we have some utility commands that you can use to find libraries within your own installation. So basically, like when you write the ESSL package, or when you write the netlib LAPACK package, you write a method like this, and you say, to get my LAPACK lib, search for all the things that start with lib LAPACK in my prefix that are shared, and recursively search. And you can make this search non-recursively. There's a lot of utility functions like this in Spack that are useful. This is really only useful if you're writing the provider library, and we kind of already have a lot of the BLOS implementations already in Spack, and so we don't focus on this. It's really the client code that we're interested in getting across in the tutorial, but this is what you would do, and it's pretty simple. And then Spack does the magic to sort of wire this up so that when you say spec sub-LAPACK.libs within the RPAC build, it knows to call this thing to get the libraries that are provided. And that's pretty much it for that part. Okay. Any questions? Nope. Okay. So this eases the task of building with lots of different BLOS implementations, especially because like the way that they're decomposed into libraries can be a really painful part of the API. Because they don't claim that it's part of the BLOS API, but it's effectively part of the API, right? Like, I mean, you have to know what libraries to link against. And it can be pretty nasty. Okay. The other thing that we provide is a way to get at subsets of libraries. So for things like HDF5, there are certain libraries that have to do with like the high-level interface, the C interface, the Fortran interface, stuff like that. And Boost is like this too. There's different subcomponents in Boost. And you may need to refer just to the high-level interface of HDF5. And so we provide, and I'm not going to get into the details of this, but we basically provide a way for you to subscript the dependency with a colon. So you can say self.spec sub HDF5 colon HL, and then it's going to give you a subcomponent of HDF5. And that works that works pretty much the same way that the BLOS and LAPACK provider interfaces do. It's just providing you a subset of libraries for the package itself. There's no virtual interface involved here. Any questions on that? And so some packages support this, some don't. But if you have a package that provides a lot of different interfaces, this is something you could consider adding to it to make it easier for things that depend on it to actually use it. And this is similarly, this is a libs object just like we got before. You can refer to .libs on it, and you can get the search flags for that, or there are lots of different convenience attributes there that you can use to get the sorts of things that you would pass to a configure line or to a build script. Yep.
If you didn't put the colon HL, you would get a superset of
Yep.
all the flags.
You'd get all the HDF5 libraries. Yeah, exactly. Yeah. And so this is a way to just filter out subsets, because often you need that in the build, right? You don't want everything that uses HDF5 to link against all the different libraries. Like if you're say a Fortran library and you're using HDF5 and it happens to have the C++ interface, you probably don't want to link against the C++ interface library. It's along with everything else. You want to use stuff like this. Okay. Same thing works for headers. So that object that you get back from spec sub hdf5:hl, it has convenience methods for headers, and so you can say hdf5:hl.headers.cpp flags, and that'll give you things that look like this. So it'll say if you ask for this in CPP flags format, it basically just puts -i's in front of all these things so that you can hand them off to a compile line. So this is for CPP flags. It might include some macros, and then the include flags down here would just include the -i's. And so you can differentiate those things pretty easily with these convenience methods and hand them off to different parts of builds. There are Spack packages that provide commands to their dependents. And so this is sort of a convention that we have among the Spack packages. We have this .command spec property that retrieves the command for that package. And I guess the way to determine whether your package should have this property or not is if you say the my package command and it makes sense or not. So if you can say the Python command about your package, right? There is a Python command. People understand what that means. So use command for that. If it's, the boost command, I don't know what that means. So don't provide command on boost. Does that make sense? This is sort of one of those optional things. And so what that looks like here is if you have a package like OpenBabel, which I believe, I actually don't know what this package does, but it requires you to supply a Python interpreter that it should use. And you do that through CMake. You say -c Python executable equals something. You can just say spec subpython.command.path to get the path to the Python command. And that's pretty readable and understandable, right? You know that you're grabbing the command from your Python dependency and you're passing it into the build. So this is just a convenient way to do that. Any questions on that? Okay. And again, this package, we know that we can get specs of Python because the OpenBabel depends on Python, right? And so this command is coming from something in the Python package. If you want to know where it's coming from, you can just do Spack edit Python and look at the code for the Python package. But this is a way that whoever wrote the Python package is providing convenience functions for the people who link with Python, right, or who build with Python. And it's available to anything that depends on Python. Okay. And then, let's see. The other things that provide convenience methods are things like, so we talked about, so the Python package actually provides a Python function globally to things that depend on it. So if I'm this class py/scipy, that's the scipy package in Spack. We prefix all the Python packages with py. And I depend on, and I'm a Python package, which is our way of, this is one of the build systems that Greg talked about. This basically implies that it depends on Python and includes a bunch of extra logic for the install method because all the Python packages are essentially built the same way. If I want to, use the Python command in my package, it's already inserted in module scope by the actual Python dependency. So if you're a dependency package in Spack, you can actually put things in scope for dependence on you. So that's like you saw in the early packages that we showed, that in the install method you can say configure and pass it arguments, right? And configure was just a freestanding Python function. That gets inserted in module scope by Spack. This is a way for packages to do it. So the Python package actually sticks this function, which is basically an executable object, in the scope, and you can call Python like this from inside your package. You don't have to do anything special like import popen or any of the complicated process management things that you would normally have to do in Python. You can just call Python like it was a function. The other thing that's useful here is we have, specs can provide attributes of their own, and so the MPI packages in Spack provide an MPI-CC attribute. They actually provide MPI-CC, MPI-CXX, MPI-FC, all the different compilers you would expect from an MPI installation. And you can use this as a compiler. So we talked a little bit earlier about how there are different ways that packages use MPI. So some packages that use MPI treat it like a dependency, right? Like if you're using the CMake find MPI function in CMake, that actually treats MPI very much like a library. And so your CMake builds will add MPI as a dependency. It'll use the variables returned by find MPI, and you typically don't use the MPI compilers directly when you build with MPI in CMake. Other builds do want to use the MPI compilers directly. And so for those, this one happens to be CMake, so it's sort of violating the convention I just described. But you can pass the MPI compiler directly to the build like this. And so all you have to say is specs of MPI, right? This thing depends on MPI. We can get specs of MPI. I can ask for the MPI CC variable from it, and that gives me whatever the path to the MPI compiler is for that package. And this is useful because I mean, you know, it enables us to use MPI in lots of different ways in Stack packages. I mentioned earlier that there is a guide. I'm not going to get into the details here, but I think this is a handy thing for people to know about. If you go to the Spack docs and you look at the packaging guide here, there's a lot of stuff here, but one of the interesting things that you might want to read is MPI support in Spack. And this sort of describes how we expect packages to use MPI in their build logic. And so it basically tells you how to set up your package to use MPI as a compiler, as a library, or however you want to use it. Those conventions are documented here. And that's under the packaging guide. Okay, back to that. All right. So more advanced packaging. The other thing that Spack packages can do is that they can set up some environment variables, either for the run environment or for the build environment of their dependencies. And so if your package uses a Python extension to build, like setup tools, we make that available. The Python package actually makes that available at build time in the Spack build environment by setting something in Python pack. So basically, if you build a Python package and you depend on other Python things, right, they're all installed in separate prefixes in Spack. But in the build environment, we add all of those different locations to the Python path so that you can use all of your Python dependencies to build. And I think this is an important distinction between something like between Spack and something like EasyBuild. If people have heard of EasyBuild, Spack does not rely on the module system to load dependencies at build time. So like our build system, we don't require modules at all. We can generate modules. We can make it so that you can use modules at runtime, but to build with Spack, you don't really need modules. Run it on your Mac, and it'll still work. You don't have to have the module environment or the HPC environment. It's geared towards a broader audience than that. And this is the kind of thing that we do to support that. We basically ensure that our build environment is setting all the environment variables get set, and we're not just loading modules